Hi there. We looked today in class at 4.3, which is definite integrals, and we looked at some properties of integrals as well as kind of a conceptual definition of what a definite integral is. Back in Unit 2, when we were learning derivatives, we talked about the fact that we utilize derivatives in calculus to find the slope of the tangent line. And so that became somewhat synonymous, right? Not perfectly synonymous. There are obviously other applications of derivatives than just finding the slope of the tangent line, but we kind of started to use them in conjunction with each other. Okay? We're going to have a similar relationship here that occurs in 4.3, only this relationship, rather than being with the derivative, is going to be with the definite integral. I know this is a definite integral because it has bounds 0 to 8. And we utilize definite integrals to find the area of a shape. And this area, or this shape I should say, is created between the function that we are given, so in this case 8 minus x, the x-axis, and then the two vertical lines found at x equals 0 and x equals 8, or whatever your bounds happen to be. Okay? And the shape that's created by that, that's what the definite integral is finding, the area, I should say, of that shape. Okay? And so with 28 here, we're just looking at that conceptual definition, right? And it asked us on 28 to start with sketching the graph. Okay? So we can see the shape that's being created. And so I'm going to go ahead and sketch the graph of 8 minus x. So I have a y-intercept here at positive 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. And I have a slope in this particular case of -1, so I'm going down 1 and over 1. Down 1 and over 1. Down 1 and over 1. And obviously, because I am hand sketching this, this is by no means going to be a perfect sketch, but it's going to give us at least kind of a rough idea of what our picture is going to look like. In fact, I think my x's scale happens to be a little bit off, so my line doesn't end up being quite perfect, but I can still see what shape I'm looking at here, right? Okay. This is a triangle. It's the area from 0, which is here, over to x equals 8, which is here, 0 to 8. And it's the shape created between the function and the x-axis. So I've got a nice little triangle here. And a definite integral is just asking me for that area. Well, the area of a triangle is 1/2 base times height. The base of this particular triangle is 8, and the height of this particular triangle is also 8. And 1/2, 8 times 8 is 32. That's what a definite integral is finding, area. And we're actually going to look in 4.4, when we learn fundamental theorem of calculus, at another way to find that area. Rather than using geometry, we're going to use calculus. Okay, the other one I picked for 4.3 here is number 44. Just to kind of look at some of the properties that we learned. In number 44, we are given two facts. We are told that the integral from -1 to 1 of my f of x is 0. And I don't actually know what f of x is, right? It could be a triangle, semicircle, rectangle, some combination of those shapes. I don't know, and honestly, it doesn't really matter for this particular problem because we're looking at the properties of it. So whatever the shape happens to be, however odd it happens to be, I know that the area from -1 to 1 is going to be 0. Okay? I'm also told that the integral from 0 to 1 of f of x dx is 5. Again, I have no idea what the shape looks like, but whatever it looks like, the area from 0 to 1 is 5. And then they asked me to find 4 other facts. The first one here is, what is the integral from -1 to 0 of f of x dx? Okay. Well, I'm told that from -1 to 1, that whole area is 0, and then I'm given a piece of that shape, that 0 to 1, right, which is part of this interval, right? -1 to 1, the whole interval is 0. Part of the interval from 0 to 1 is 5. And so this one's asking me for -1 to 0. It's asking me for the other piece of that interval. Okay. Now for some people, their minds immediately are able to jump to it and go, oh, well if -1 to 0 is a number, And 0 to 1 is another number, 5. So negative 1 to 0 is some unknown number. 0 to 1 is 5. For the total, for all the way from negative 1 to 1, for the total to be 0, this negative 1 to 0 has to be negative 5. It's the only way you could have one piece of a whole shape, add to 5, and get 0. Negative 5 plus 5 would get 0. Okay, for other individuals, you might not be able to immediately make that leap. It might be helpful to give yourself a picture to look at. Again, we have no idea what f of x looks like, but give yourself something to look at. Okay, so this might be my f of x here. I don't know. And this will be negative 1 out here, and this will be 1. And I'm told that the whole area, negative 1 to 1, this whole area in the entirety of this shape, this little curved piece and this curved piece, the whole thing's 0. I'm told 0 to 1 is 5. This piece here is 5. So the question is, what would this piece have to be, the negative 1 to 0 piece? What would this piece have to be to give me 0 as a total? Well, that piece would have to be negative 5. And then you'd have a total area of 0. It might be a little bit easier. And again, that function, I made that up. I don't know what f of x looks like. I just decided that was my f of x, just so I'd have something to label, so I'd have something to look at. Okay? Okay, in in letter B, they ask us for what is the integral from 0 to 1 of f of x dx. Well, I know that's 5. Minus the integral from negative 1 to 0 of f of x dx. Well, I just found that one. That's negative 5. So it's 5 minus negative 5 would be 10. Okay. In C here, we are using one of our properties. The property says that if you have a coefficient, this 3, you can pull that outside. You can treat it after the fact. You can focus in on the integral of the f of x piece and then times the 3 at the end. Right, that's what that property allows us to do. So we're going to go ahead and pull this 3 out, and we're going to focus in on what's the integral just of negative 1 to 1 of f of x. Well, negative 1 to 1 of f of x, remember, was 0. And so 3 times 0 is 0. And then in D, we utilize the same property. In D, we are finding the integral from 0 to 1 of 3 f of x dx. Well, again, I can pull that 3 outside. I can focus in on the f of x component and just ask myself, well, what's the integral from 0 to 1 of f of x dx? 0 to 1 of f of x dx is 5. And 3 times 5 is 15. Okay. And that's 4.3.